With that, please help me welcome our speaker for the morning. Hello, Timothy Thompson. So good
Hello.
Thank you for joining us. Welcome, Palomar Observatory. And I really appreciate you talking to us this morning. Tim has been a volunteer at Mount Wilson Observatory now for 41 years. Mike, you're going to have to work hard to catch up to him. Mike's got 20 years here. It's going to take a while. And just think how great the pension benefits must be.
I'd be over 100, Steve.
Details.
We've had tour guides up to age 93, so don't hold back.
There's a little ways to go. Hang in there. Currently, Tim serves the observatory as session director, observatory docent, and institute trustee. He holds BS and MS degrees in physics from California State University at Los Angeles, a tournament-rated chess player. Tim is past president and board member of the Los Angeles Astronomical Society. Tim, again, thank you for taking the time to speak with us. And everyone, please, you can type questions into the chat, and we'll take questions at the end of the presentation. For that reason, right now, I'll ask everyone to turn off their microphones. And with that, Tim, please, the floor is yours.
Oh boy.
Oh boy.
Well, let's see if I can make this magic work here. Okay, you should be able to see my my slide. So
Yes, we can.
I christened this talk in 2019 for the, what's that? You can see? Okay, good.
Yes, I can see the.
I christened, okay, good show. I started this in 2019, which was the year of the International Year of the Periodic Table for the Mount Wilson Public Lecture Series. And I've done it a few times since then. I find it an interesting topic, and hopefully you will too. And if you don't, go away. And so now let's see, how do I, there we go. And so this is Dimitri Mendeleev, who's the guy who gets the lion's share of the credit for creating the periodic table of the elements as we know it. And you can see here his original published version in Russian. But, the lone genius discovering these things is a myth of science. It was never happened. De Chanquois, I think that was his name. His name is cut off. Discovered the periodicity of the chemical properties of the elements back in 1860. Lothar Meyer, I think it was in 1862, published a version of the table, and it was Mendeleev who finally finished it and kind of put it in the most detail, and he gets the credit for it, but he was not the only one working on that problem. Here's the periodic table of the elements with time. There was a Bronze Age and a Stone Age and an Iron Age and all that good stuff. And so the metals, you can see these dark kind of magenta color. Those are elements known in antiquity. And you can follow the color code and see which elements were discovered as time went by, when Lavoisier published his table of the elements in 1789, and Mendeleev, Seaborg, and up to now. And the elements 113 through 118 are relatively recent, having been added in the last 10, 15 years to the periodic table. And this, of course, is the periodic table is the magic guide chemists use to all the elements. And there's a copy of the periodic table hanging in every science classroom in the world, and nobody knows what it is. They look at it and say, yeah, there's numbers and elements, and who cares? But where did those elements come from? That's what we care about, and that's what we want to talk about today. And so I'm going to combine the topics of stellar evolution and the origin of the elements. And I'm going to point out that stars are the fundamental element of astrophysical evolution. And by that, I mean, you think of the universe the way you would a painting, where the background of space-time is the canvas for the painting, and all the stuff in the universe is the paint spread out on the canvas. So the universe will evolve because the space-time evolves, as in the expansion of the universe, which I will not talk about, or it evolves because the stuff does, and that's what I am going to talk about, the stuff, the paint. And it evolves almost entirely because stars evolve. So the evolution of stars dominates the evolution of the universe, aside from the expansion of space-time. And that brings us to big deal number one. Excuse me. Pay attention. Everything we know about stars comes from the light, and that's all we get. And all of you who are astronomers, amateur astronomers, you know you can't go out there, pick up a teaspoonful of star stuff, dump it in your lab, and look at it. It doesn't work. We only have light. Now, of course, we've extended that to X-rays, ultraviolet, infrared, but it's all light. It's just light your eyes don't see, and that's all we get. So everything we know about stars comes from the light, and it's really one of the amazing things about astronomy is that you can learn so very much about something, and all you get to do is look at the light. Now, speaking of light, stars have brightness and they have color, both of which you can measure. And you can see that here in this Hubble Space Telescope image. The bright stars, there's some red stars, blue stars, the really bright ones with the diffraction spikes are up front. Lots of dim stars in the background that are much farther away. For the most part, in this image, the brightness is controlled by the distance, but that is not always the case. So the temperature of the star defines both its color and its brightness per unit surface area. The color is demonstrated here, and while you're used to the idea of red being a hot color, because of flowing red lava, it's the opposite for stars. Blue is hot and red is cool. The temperatures are shown to you here in degrees Fahrenheit and in degrees Kelvin. Astronomers in your daily life, you use Fahrenheit, so now you can see both of them. So the O-class stars, for instance, can get pretty hot, up to 100,000 degrees Fahrenheit. It's important to remember that the brightness control is per unit surface area. That's going to become important later on. So this is a plot of brightness and color. On the vertical axis, you see luminosity. On the right side, it's absolute magnitude, which is the apparent magnitude, or how bright something appears from a standard distance, always 10 parsecs. And over on the left side, it's luminosity compared to the sun, where the sun is just 1 and everything else is either brighter or dimmer. And you have spectral classification along the top, and the color as a B minus V, means blue filter minus the V filter on the bottom. And it's worth remembering how the magnitude scale works, where the bigger the number, the dimmer the object. So if that B minus V is a positive number, it means the blue magnitude is bigger than the V magnitude. V is a longer wavelength, as you can see in the text over on the left. It's redder. And so if this number is positive, it means that the red end is brighter, and so the star is increasingly red. And if it's negative, then it's increasingly blue. And hence the color goes from blue to red, from left to right across the bottom. And you will notice that this is a highly non-random collection of dots. You might naively just think, well, a star should be able to have any brightness and color that it wants. And you would expect just a scattering of dots all over a plot like this, but that's not what happens. The purple lines indicate what are called luminosity class, giants, subgiants. The main sequence is labeled that way because most stars lie along that curve, this curve, which runs up the plot from lower right to upper left. And of course, the dots are color coded to match blue over here and red over here. And that leads us to the next big deal. This is a highly non-random distribution. It's caused by stellar evolution. So you look at the sun, say number one, the sun. So the sun's going to be here, roughly. And so you look at the sun, you come back in a billion years, and the dot will have moved. The sun will have changed. It'll be bigger and brighter. And as the years go by, you keep looking at the sun, its dot will propagate in the plot with time. It will move up here and it will come over here and squiggle around like this and go over here. And so you can compute all those dots and then connect the dots and create a plot of how you expect the sun to evolve with time. And it's that connect the dots methodology that explains why this distribution looks the way it does. And I point out in saying that stars can't just have any brightness and color that they want. The red dwarf stars are down here. They're red, but they're dim because they're on the low end of the brightness scale. And the red giant stars are up here. They're the same temperature, but they're orders of magnitude brighter, factors of hundreds and thousands brighter. And there are no red stars in between. This is a discovery that was made at Mount Wilson Observatory by Walter Adams while he was busy doing something else, and tripped over the fact that all of his red stars had absolute magnitudes in two classes, two clumps, and nothing in between. And he correctly figured it was size. The bright ones were bright because they were big, and the dim ones were dim because they were little. So hence the difference between red dwarf and red giant stars is a discovery of Mount Wilson Observatory, which I thought I would just mention while I was on the topic of Mount Wilson, which I wasn't, but I always am. And so here is one of those connect the dots diagrams that shows you how we expect the sun to have evolved and how it will evolve. And as you know, there's nuclear physics going on inside the sun, and we're going to go into that in some considerable detail. But the sun starts out as what's called a T-Tauri pre-main sequence star. The T-Tauri class of variable stars is also a discovery of Mount Wilson Observatory by Arthur Joy when he was looking through decades of data from the 100-inch and 60-inch and realized that he was seeing a class of variable stars. But they're on their way to becoming regular main sequence stars, and they haven't really made it yet. So you can see there's a dot down there when the sun's 10 million years old. As it grows, its line moves vertically, so it gets dimmer and dimmer, but stays the same temperature. And then eventually, after 10 million years, now its temperature goes up, its brightness goes up. And you look at, there's in 12 billion. So right now, the sun is 4.5 billion years old. When it's 12 billion years old, it will be 10 times brighter than it is now. Probably in 2 or 3 billion years, it'll be maybe twice as bright as it is now. So we really only have a couple of billion years to figure out how to move ourselves. Excuse me. How to, move to Mars, Jupiter, something. And find a more comfortable place to hang out, because once the sun doubles in brightness, the Earth won't be so is that the sun is fusing hydrogen into helium in its core. And we'll go into that in some detail in a few minutes. When it runs out of hydrogen in its core, the region of fusion propagates to a shell that surrounds the core. And that moves outward as the hydrogen fuses and the ash falls down onto the helium core. And the sun becomes both brighter and cooler because it's expanding. So its outer layers cool while its core gets much hotter. And eventually the super hot core ignites and you start fusing helium. That turns off the hydrogen fusion in the shells. Now you have just helium fusing in the core. You wind up at what's called the horizontal branch of the HR diagram. And then the sun does that red giant thing again, only this time it's called the asymptotic giant branch. And again, outer temperature goes down, inner core temperature goes up, its color gets redder and redder, and eventually goes through its planetary nebula phase. And then the nebula kind of drifts off into the interstellar medium, and you wind up with a white dwarf star down on the lower left. So this is a diagram of how we expect the sun to change as the billions of years go by. And remember, we've only got about 1 billion or 2 years to take care of ourselves in this scenario. So tell your congressman, get busy on this. Time is limited. So here are color magnitude diagrams for M3 and M13. So you can see that these are globular clusters. So all the stars form at about the same time. So their state of evolution depends on their mass. So for instance, the main sequence is this thing down here. And this turnoff point, this is where the main sequence would normally run up, like you saw on the diagram before, to the left. But those high mass stars up here have all evolved off the main sequence. They become red giants. This is called the turning point. And you can computationally figure out how the cluster ages. And this black curve you see through the points gives you an age for the cluster of roughly 12.6 billion years. This second line over here on M3 is the asymptotic giant branch. This thing is called the horizontal branch, even though it tends to be kind of vertical in most places. And there are no dots in this gap because that's the Cepheid instability strip. Stars with that particular mass go unstable and become variable stars, and their dot moves around on a daily basis, and you can't put them anywhere on a diagram like this. So they're empty. There aren't stars there. These are called blue straggler stars, and in the core of a globular cluster, stars can tend to merge together and rejuvenate and give rebirth as if a new generation of stars is being born. Not many of them, but they show up in all globular cluster color magnitude diagrams. Alan Sandage discovered the main sequence of M3 because they're too dim, using the 100-inch and I think the 200-inch telescope as well in 1951. And Harlow Shapley discovered the red giant branch of the M13 while he was busy trying to figure out what the Milky Way was. And he did that using the 60-inch telescope at Mount Wilson. And so they were just learning about globular clusters back in the 30s, 40s, 50s, et cetera. Now we know a lot more about them, but we're still learning. Another thing you do with light, of course, is spectroscopy, and that's the real tool for astrophysics. This is a photographic spectrum of the solar spectrum, photographic image of the solar spectrum, the KNH calcium lines. You have to remember that you're looking through Earth's atmosphere. So before you go running out and saying, I found O2 in the atmosphere of the sun, no, actually you found the Earth's atmosphere. Congratulations. That was a big discovery. And so you do have to be a little careful about what you're doing. There's lots of lines. This is what you would get back during the early 1900s, late 1800s, up until fairly recently, where you get a photographic spectrum and analyze it. Nowadays, we use digital spectra, and that's a digital copy of this spectrum you see on the bottom. And as you can see, for instance, over here on the left, it's hard to tell in the photographic spectrum, but the lines that have shape, there's a brightness distribution inside those dark lines, and that depends on the physics of what's happening. How strong is the reaction of the atoms? Is it self-emitting? Is it self-absorbing? What's the pressure broadening of the lines? There's a lot of physics encoded in this digital spectrum. Remember, light is all we get, so you have to get everything out of it that you can, and spectroscopy is the way to do that. And we can tell what those elements are because, and here's another periodic table, each element has its own very particular spectrum. These are emission spectra. That's how it was discovered in chemistry labs during the mid-1800s. If you heat it up, take a pure element like pure beryllium, heat it up, and you get these colors is all you get. So when your eye integrates them, it has some characteristic color. But when you look at the spectral features, no other element looks like that. It might look like hydrogen looks like that, but the hydrogen line you see is bumped around. So you can tell what element you're looking at. The only problem is when you're looking at an image like this, they're all superimposed on top of each other here. So you have to do a little work to figure out which pattern goes with which element, but you can do it. It's just requires work and tell which elements that you're looking at. So why do stars evolve anyway? Why don't they just sit there and stare at you for a billion years or whatever? It's because they are nuclear pressure cookers, and that's going to lead us in to where the elements come from. This is a cutaway diagram of the solar interior, the sun being a fairly typical star, although typical in spectral class. I want to remind you that the sun is bigger than 95% of the stars around. So it's considering size, the sun is actually a very large star. Most stars by far are much smaller than the sun. They're mostly red dwarfs. You're already in the 95th percentile when you get to stars like the sun. So when people say it's an ordinary average stars, no, 95%. We come from a big planet, the biggest of the little planets around a big star. So you have no inferiority complex worries because of the planet and star you come from. But if you go out and you stare at the sun in the few seconds before you burn a hole through the back of your head, and everybody knows that you did something really stupid, so don't go stare at the sun. But if you did that, what you would see is the photosphere. And as you can see in the diagram here, the density of material in the photosphere is almost like space. You have to go up 50 miles in Earth's atmosphere to find such a low density, and 62 miles is where you officially go into space. So it's really interesting that while it's so incredibly bright and hot, it is very not dense. The interior of the sun, say the outer third, is a convective zone where heat transfer is controlled by the physical motion of the plasma. The inner 2/3 or so is the radiative zone where the plasma is too hot. You can't move energy fast enough by moving the gas, so you get radiation transfer of the energy instead. On supermassive stars, that actually inverts and you get forced convection on the inside and radiative transfer on the outside. It's really weird. But for the sun, this works fairly well. But even at the bottom of the convection zone, you're still less dense than water. But as you get towards the core, things get denser than the densest elements on the Earth. And now you run into a problem. Am I looking at gas? Am I looking at solid? Am I looking at liquid? You're looking at a plasma, and just don't worry about whether it's gas, solid, liquid, whatever. It's another state of matter because it's really hard to tell what you're looking at. And you notice the core pressure is 1 trillion Earth atmospheres, which means 14.7 trillion pounds per square inch. And the temperature is about 15 million kelvins or 28 million degrees Fahrenheit. So if somebody asks you, why don't we send a probe to study the core of the sun. Now you know, 14.7 trillion pounds per square inch and 28 million degrees. That's why we don't do it. And if you can figure out a way to do it, you might get 2 Nobel Prizes instead of 1, just because it's a fantastic discovery. But it's the conditions down in the core that are high enough, hot enough to give you nuclear fusion. So this is what stars phenomenology look like when they evolve. A star like the sun will become a red giant, a planetary nebula, eventually a white dwarf, and the planetary nebula will dissolve into the interstellar medium. A much more massive star, say more mass than about 8 solar masses, will become a red supergiant. It'll actually blow itself to bits in a supernova explosion and maybe leave behind a neutron star, red, or a black hole. But in both of these cases, planetary nebula or supernova, remember that the elements are inside the star and we need them to get outside. And this is a way to get the elements outside. I'm going to talk about that in more detail a little bit later. Here, the diagram that's really interesting is the one on the bottom. You have a red supergiant star like Betelgeuse, for instance, which is roughly the same diameter as the diameter of the orbit of Jupiter in our own solar system. But all the nuclear action is going on way down deep in this little pea-sized thing in the core. The blue scale bar is the diameter of the Earth. So this core is on the same scale of size as the Earth is in a star that's the same scale of size as the orbit of Jupiter. So the difference in spatial scales is enormous, to say the least. And now you have nested shells where you're fusing hydrogen into helium. That falls into a shell where the helium is fusing into carbon, which falls into a shell where it's fusing into neon and oxygen, which falls into a shell, and so on until you get iron down at the core, and then that's where things have to stop, as we will see later on. So now we come to the point where the origin of the elements comes into the tale. In the original interpretation of Big Bang cosmology, all of the elements were created in the Bang, because up until then, nobody had figured out how you make elements. Nobody could find a way to do it. And when Big Bang cosmology came along, they all thought, great, the Bang, we'll do it in the Bang and we get all the elements and we're done. It works perfectly. Well, turns out not to work at all, not only not perfectly. So this is our modern understanding of Big Bang cosmology. And for those of you who are really interested in it, the first 3 minutes, which is a popular level book written by the late Steven Weinberg, is really about the best you're going to get for describing the first 3 minutes of the Big Bang. It's a really good book, still in print because it never goes away. So about 1 microsecond after the bang bangs, whatever the bang is, you form protons and neutrons. And about 10 milliseconds after the bang, those neutrons and protons begin the first era of nuclear fusion. And that goes on for about 3 minutes. So by the time you get to the 3-minute mark after the bang, you're all done with that. And that's where you get the era of what's called Big Bang nucleosynthesis that looks like this. So you have only neutrons and protons. Free neutron floating around on itself is unstable and will fall apart into a proton and an electron in about 15 minutes. If you bash the neutron into a proton, you get what's called a deuteron, which is a proton with a neutron stuck to it. If you bash 2 protons together, you will still get a deuteron because one of them will turn into a neutron. So you always wind up one way or another with a proton that's got a neutron stuck to it, or a deuteron, which is the letter D here in this square. Now there's a bunch of nuclear reactions that can go on. You can, in several different ways, you can hit it with another deuteron, you can hit it with a proton, it becomes helium-3, which means 2 protons and 1 neutron, or it might become hydrogen-3, which is 1 proton and 2 neutrons. And that, through various means, can become helium-4, which is stable. Now you can bash helium-3 with a helium-4 and get a beryllium nucleus that's radioactive and decays, or you can bash that, make it lithium, but the lithium, you bash that, becomes helium. You can see the chain of reactions on the diagram here. The result is that Big Bang nucleosynthesis creates about 75% helium-4, 25%, excuse me, helium-4 and 75% hydrogen, and a tiny smattering of deuterium, the deuterons, and some lithium and some beryllium, but hardly enough to actually measure and discover. It's all hydrogen and helium. And the tritium, of course, is radioactively unstable and decays away and goes. And so this is where the hydrogen and the helium comes from Big Bang cosmology, but nothing bigger than that. We're all done with the Big Bang. You just get hydrogen and helium. That's what the first generation of stars have to work with. They've got nothing in them but hydrogen and helium. Later generations, like the sun, as you saw from the spectrum, have all kinds of stuff in them. But the very first stars, which actually your next speaker, Avi Loeb, did quite a bit of work on primordial stars. He was one of the pioneers in studying how the very early stars work in the post-Big Bang universe. So here you wind up with the reaction that takes place in the sun. This is what provides most of the sun's power. You take a couple of hydrogen nuclei, that means 2 protons, you bash them together and they throw away a positron, get rid of a positive charge, you wind up with your bottom. The gray ball is a neutron, the red ball is a proton, and you bash the neutron with a proton and you create helium-3. You bash a couple of helium-3s together and you wind up with helium-4. I'm leaving out a whole bunch of stuff that can happen. And just to make the point, here is one of my textbooks on nuclear physics. It's thick. You see, it's kind of big, right? And I'm necessarily leaving out a whole lot of stuff, or we'd be here until tomorrow talking about nuclear physics in the stars. But this particular diagrammed reaction is responsible for about 85% of the sun's output energy. Then there are other proton-proton reactions where you bash things with helium instead of a proton or whatever, and wind up with the same thing in the end, helium-4. The reaction over on the right is often called a catalytic reaction, where you start with carbon-12 and you go through stable nuclei and radioactive nuclei, you bashing with 4 protons, and you wind up in the end, if you start with carbon-12, you wind up in the end with another carbon-12 and you're throwing away a helium-4 nucleus. And this is another way to make helium with 4 protons, but this time you're not doing it directly the way you are with the proton reaction. The CNO cycle requires much higher temperatures to work than you see in the sun. So it only produces about 2% of the sun's energy. Is not terribly important in the sun, but it is in higher mass stars. And these 2 reactions were both discovered theoretically in, say, 1938, 1939 by Bethe and Critchfield, Hans Bethe, and I think he worked with Critchfield on the proton-proton reaction and did the CNO himself. So they knew this reaction would work only in the 1930s. And of course, they still hadn't come up with the idea of creating elements, creating the heavier elements this way. They just knew that these reactions would give you some energy. And that gives us pause to pay attention to big deal number 3. If you look at the red number up on the upper left, if you are a typical proton running around inside the sun looking for something with which to fuse, it will take you 8 billion years to do so. It's a very slow reaction, which requires 5 million kelvins or 9 million degrees Fahrenheit to get going. But if you just add one neutron, now if you want to bash that with a proton, it takes you only 1.5 seconds to do the same thing. So just adding a neutron changes 8 billion years to 1.5 seconds, which is really pretty amazing and shows you how incredibly sensitive these reactions are to temperature. And the 8 billion year time scale for proton fusion is what controls the time scale for the process, because 1.5 seconds and 240,000 years are both very small by comparison. It's that time scale which allows the sun to sit around for 10 billion years, allows it to last for at least 4.5 billion years so we can be here. If you change that reaction rate just by a small amount, the sun only lasts 1/10 as long, and we never show up, right? Until if it takes 4.5 billion years to get intelligent life, you don't get it. You don't get it unless that time scale for proton bashing is long enough. Secondly, while it's very common for everybody to say that nuclear reactions power the stars, that is not only wrong, it's exactly wrong, because it's the complete reverse of what actually happens. Nuclear reactions do not power stars. Stars power the nuclear reactions. Remember, proton-proton fusion won't happen until you get to 9 million degrees Fahrenheit. And those 9 million degrees have to come from somewhere, and they can't come from proton-proton fusion because it's not happening yet. It comes from gravitational contraction. As the star forms and the contracting cloud shrinks, the center core gets hotter and denser, and now you have mechanical pressure because the hot stuff is moving around faster, and you have thermal radiation pushing outward. And those two forces oppose the contraction of gravity, but not enough. Gravity wins every time, and it will just shrink all the way down to white dwarf, neutron star, black hole, and go away, and do so very quickly. So you'll never have stars at all. But once you turn on nuclear fusion, you are creating a lot more electromagnetic radiation, much higher in energy than the temperature. It's non-thermal radiation. And that extra outward push stops the contraction, brings the star into balance, into equilibrium, and allows it to sit there for as long as the nuclear reactions are going on. And that, again, is why there's time enough for people to show up, planets, whatever, for the universe to do something interesting in 4 billion years, because otherwise there wouldn't be any stars at all. So there is an intimate connection between the details of the nuclear physics and the history of the universe. The biggest things in the universe and the tiniest things in the universe are intimately connected in that way. But so this is how we make helium, more helium out of hydrogen, but we already had helium from the Big Bang. So we're not doing anything really exciting here. We're just creating more helium. We already had helium. What about the bigger stuff? Aha. That brings us to the triple alpha process. If you bash 2 helium-4 nuclei together, they will give you a nucleus of beryllium-8, which does not last for very long before it falls apart because it's unstable and reverts to 2 helium nuclei. During that small period of time, you must bash the helium-8 nucleus with a 3rd helium-4 nucleus, and now you get carbon-12, and that is stable. And that brings us to yet another big deal. you cannot create the heavier elements unless you can get past the barrier presented by fusing helium. You notice the time scale for the beryllium-8 nucleus is 8 times 10 to the minus 17 seconds. For those of you who are not into scientific notation and exponents, that is 8 100,000ths of a trillionth of a second, which qualifies as being tiny by almost anyone's standard of time. That's not long. And during that period of time, you're not going to get many collisions with the helium-4 nucleus unless the temperature is really high, like 100 million kelvins. And secondly, the reaction was always thought to be impossible. It simply doesn't work. However, if the beryllium-8 nucleus is created in what's called an excited state, which means with more energy than it should have when the helium-4 nuclei fuse, then you can stick a third helium nucleus onto it. That is the discovery that was made by Fred Hoyle, who realized the impossible reaction becomes possible if the beryllium-8 nucleus is excited instead of being in its ground state. And that, as Willie Fowler pointed out, is a Nobel Prize worthy accomplishment. But Fred Hoyle was very good at making people not really like him all that much. And most of the people on the Nobel Committee didn't really like him, and they didn't appreciate his attitude towards Big Bang cosmology. They just decided, no, we're not going to give Fred a prize. They gave Willie a prize, but they didn't give Fred a prize. And so there you have, but it was Fred who figured this out. So once you've got carbon-12, now you are home free, because you can bash the carbon with a helium and get oxygen, bash the oxygen with the helium and get neon, bash the neon with the helium and get magnesium. And there's a whole bunch of, other stuff going on. Like you can bash carbon and oxygen and get silicon. You can bash a couple of oxygens and get sulfur, bash a couple of silicons and get iron, and a whole lot of other stuff. Remember the big thick book I showed you? Here it is again, big thick book, right? There's all kinds of stuff happening here, which we're not going into, but these are examples of now how you go through the chain of reactions to create the heavier elements. And this works up until you create iron. The diagram on the upper right is an energy diagram, which shows you that for light elements, you get energy out of the reaction by fusing them together into heavier elements. But the heavier the elements are that you fuse together, the less energy you get out of the reaction until you make it to iron, when you get no energy out of it at all, and it no longer works. Heavier elements than iron, you get energy not out of fusing them together, but fission, breaking them apart. And in this case, the lighter the element gets, the less energy you get out of it until you get down to iron, which is the basement. You don't get any more energy. So everything works until you have iron, and after that, you're in trouble. So this plot in the bottom shows you the relative abundances of the elements in the universe. That's a logarithmic scale on the left, the vertical scale. So that shows you powers of 10. The sawtooth structure is real, and the even elements outnumber the odd elements because helium-4 is the key, and it's an even number. So you wind up with more even elements than you do odd elements by a relatively small amount. But we've made it up to iron, and we need to make heavier elements than iron. How do we do that? So we have two problems. One is we need to create the heavier elements. The other is that the elements we have created are buried in the star, and we don't want them buried in the star. We want them out here where we are so we can have books and bookshelves and us and computers. It doesn't do it any good to have the elements in the star. So we go back to this diagram that we saw before. We make planetary nebula, we make supernova explosions. But remember that tiny little core in the great big red giant star is where all the action is. And when it blows up as a supernova, you destroy all that. You don't get any of those elements. They're destroyed. So you've got to get those elements into the outer layers of the star so that you can spread them around. And that means you have to have convection currents inside the stars, and you do. Red giant and supergiant stars especially have prodigious convection currents, and the convection currents in Betelgeuse, when an extra large amount of gas was spit out from the star and cooled into dust. Those convection currents dredge up elements from the core, spread them into the outer layers of the star, so that when you form a planetary nebula, you're now seeding the interstellar medium with all those heavier elements. That's what the first generation of hydrogen and helium only stars did, so that the next generation of stars could have some stuff in them that were created by that first generation, and so on, as each generation of stars creates more elements to increasingly enrich the interstellar medium. So planetary nebula and supernova explosions are one way to do that. And here are some examples of planetary nebula, because you have to have pretty pictures in every talk. And so here are my pretty pictures. Cat's Eye Nebula on the lower left is a fantastic object to view in either the 60-inch or 100-inch telescopes at Mount Wilson Observatory, if you choose to get yourself on an observing session. Either join one of our public ticketed nights or get your own group together. Details on the Mount Wilson Observatory webpage. My favorite of this bunch is Abell 39, the one bottom center, because it's the perfect example of why they're called planetary nebula. It's round like a planet, it's fuzzy like a nebula, therefore it is a planetary nebula. And Abell 39 is an interesting one because if you look in the upper right quadrant, there's a little fuzzy thing here, and that is a background galaxy millions of light years away. You can actually look through the planetary nebula and see a galaxy way, way off in the background that just happens to be in the line of sight. And this Hourglass Nebula, one high school astronomy class I'm familiar with, instantly decided that this is the eye of God staring at you, and so watch yourself. So there you are, nice planetary nebula and the eye of God. So another way to get those elements out of the star is supermassive stars. In the lower right here, we have what's called a Wolf-Rayet star, which is 30, 40 solar masses, 20 to 40 solar masses. They are so bright and so unstable that light by itself provides enough pressure to simply blow away the upper layers of the star. And so this is, but now has probably about 9 solar masses, which means we've got 16 solar masses of stuff that has been spread out into the interstellar medium. They're very effective at recycling the elements that are in the star, but 9 solar masses is still big enough that it will be a supernova someday. Eta Carina is on the upper left, and that's a binary star, which probably consists of a very, very massive luminous blue variable, about 100 solar masses, and a large Wolf-Rayet star, say 30 solar masses. And it did something suddenly like the star you see on the lower right. It hiccuped, coughed, puked, whatever it did in 1843. It was called a supernova imposter event, because when it first happened, everybody thought, wow, it blew up, supernova, but it didn't. It was a Wolf-Rayet star doing its thing, and that the cloud of gas, that double-lobed structure that we see around Eta Carina now, which we can see the proper motion of. You take a picture of it and take a picture a year later, you can see that the filaments have moved. It's expanding very fast. It's what it was generated by the Wolf-Rayet companion, which did its thing. And so this is another way. that we get the elements recycled, get them out from inside the star to where we want them and need them, where we are. But where do the heavier elements come from? We still haven't figured that out yet, but this diagram is what in the Sherlock Holmes business we call a clue. So take a look at that. Say, well, I wonder what that could be. And it could be a merger of neutron stars. Now, remember back in 2017, the LIGO people caught the gravitational wave signature of merging neutron stars I think it was for the first time, actually. You can see in the bottom plot, there's a frequency in hertz and time. This scale goes down to 10 seconds before the merger event. You can tell the difference between black holes and neutron stars very easily because the gravitational wave signature of neutron stars will go out a whole minute. This only goes to 10 seconds. We can trace this out a whole minute. With black holes, after about 1/10 of a second, they're all done. So that's really easy to tell the difference. But in this case, at 1.7 seconds after this gravitational wave event was registered, both the Fermi and integral gamma ray monitoring satellites detected a gamma ray burst simultaneously. 1.7 seconds is not much time. That's really indicative of a coincidence. When black holes merge, you don't see anything except gravitational waves. But when neutron stars merge, you get a flash. And so they could tell with the gamma ray satellites where approximately on the sky would that flash be. And instantly everybody looked for the flash to catch it as early as they could. And that was indeed discovered by Carnegie astronomers using the Henrietta Swope telescope and at Las Campanas. And here's a discovery image. The NGC 4993 is the galaxy in which the neutron star merger happened. And as you can see, the flash is pretty bright, typical supernova type behavior, although they call it a kilonova this time. And we're really running out of adjectives. We've got supernova, hypernova, kilonova. We're going to have meganova next or something when they discover it. Running out of adjectives. And there it is up here, SSS 17A. And there's Henrietta, who is a rare commodity because Henrietta was a rich astronomer. And you don't get rich being an astronomer. But her father was a high mucky muck in the General Electric Corporation. He might even have run it as chairman of the board for a while, and had a lot of money in stocks and left them to her. So she got rich through her inheritance. And she gave, I think it was $640,000 to pay for the Henrietta Swope telescope. She didn't name it Henrietta Swope. Carnegie did, because she's not that egotistical. I am. If I'm Thompson telescope, fine. I'll go with that, but not Henrietta. And so how do you do that? This is what's called neutron capture processes. And on the left, we have the slow, and on the right, we have the rapid, the S and R processes. And the S and the R, slow and rapid, are a comparison between the time scale for bashing neutrons and the time scale for unstable radioactive nuclei to decay. And so if you are bashing the nucleus with neutrons much slower than the radioactive decay time scale of the nuclei, they have an opportunity to radioactively decay into lighter elements, which you can then bash with neutrons and build up the whole family of isotopes of the lighter elements. But heavier elements decay radioactively extremely fast, a fraction of a second. So there's no time for the slow process to work. You need to pile on the neutrons really, really fast in order to get the really heavy nuclei. You just can't build them up with the slow process, but you can with the rapid process, which is diagrammed over on the right. And we're looking at decay timescales that are like 1/100 of a second, 10 milliseconds. And so you really need to pile on dozens of neutrons in a mere 10 milliseconds. You don't have a lot of time to sit around. But as you might guess, because they're called neutron stars, there's no shortage of neutrons when you merge two neutron stars. And it's an extremely energetic event. So temperatures are in billions of kelvins and things are moving around real fast, and you can pull it off. So you do it by a series of slow and rapid neutron captures. And that brings us to another periodic table where we see where do these elements come from. And the color coding tells you dying low mass stars, exploding massive stars, human synthesis, because they're artificial elements. This is technetium. And as I will point out in a moment, that's not exactly correct. Hydrogen and helium come from the Big Bang. You see lithium, some of it comes from Big Bang. Beryllium is almost always called cosmic ray fission. There's no beryllium left over from the Big Bang. There's no beryllium that survives, and boron too. They don't survive nuclear processes in stars. So when you saw the abundance of the elements plot, beryllium and boron are almost not there. We're way down in the pits, because you only make them by cosmic rays bashing into nuclei in the interstellar medium. They're really hard to make. And of course, merging neutron stars is the purple thing. And there are a couple of elements of interest here. One of them is technetium, which was discovered in the laboratory and was, I think, Emilio Segre detected it and named it technetium after the Greek root for technology, because it was technologically created. It was the first element to be found and created in a laboratory. But in April of 1952, Paul Merrill wrote a paper for the Astrophysical Journal in which he combined his data from the 100-inch telescope and data taken by Ira Bowen with the 200-inch Hale telescope at Palomar. Bowen was I think he was the first director, but he was the director of combined Palomar Mount Wilson observatories during the era from 1949 to roughly 1975, when they were managed by a single unit. And then they went their separate ways, Caltech and Carnegie. So he was the director of both observatories simultaneously. And what they saw was technetium emission or technetium absorption lines in the spectra of what they called S-type stars, which that type no longer exists. R, N, and S are obsolete spectral classifications. They're red giant stars, is what they are, red giant and supergiant stars. And said, well, he pointed out, well, it's a radioactively unstable isotope. It has a short half-life. There shouldn't be any. You should never see technetium in a stellar spectrum. So maybe there's a stable isotope we don't know about yet. There isn't. There are no stable isotopes of technetium. His suggestion number 2 is the winner. Says maybe S-type stars somehow produce technetium as they move along. And of course, he also suggests maybe S-type stars are weird and temporary. They're not. So this was in April 1952. The landmark paper by Burbidge, Fowler, and Hoyle was not published until 1957, after Hoyle had solved the triple alpha barrier problem. This was in 1952, when the idea of nucleosynthesis was still in its infancy, really wasn't a big deal. So this, to the best of my knowledge, is the first smoking gun evidence, if you will, indicating the possibility of nucleosynthesis inside a star, because for the first time, you've seen absorption lines from a radioactive element with a short half-life that should not appear in a stellar atmosphere, but does. And you got to figure out why. And his number 2 suggestion, maybe they make it, is exactly the correct one. It's making technetium in a rapid neutron capture process inside the star. You can do some of that inside supernova explosions, red giants are. Most of it you need merging neutron stars. The other element of interest is gold. Now, this illustrates how you pile the neutrons onto an iron nucleus, and you can turn it into gold. But their wording is kind of interesting because it says, well, you capture some of the neutrons, but you can see iron has 26 protons and 30 neutrons, while gold has 79 protons and 118 neutrons. You're not just piling on some neutrons, you're piling on a lot of neutrons really fast in order to create gold. So when you bash two neutron stars together, you create gold, and gold is worth something. And to be precise, the gold created in those bashed neutron stars, somewhere between 50 to 70 Earth masses of gold, according to Business Insider in 2017, had a market value of $100,000 trillion. Now, I think for fairly obvious reasons, if you dump 50 Earth masses of gold onto the market all at once, that would not be its market value. But it's 130 million light years away, and it's a gas. So getting your hands on it is going to be a little bit difficult. But we know where you can find 50 to 70 Earth masses of gold if you're really inclined to go out and get it. And I'm going to conclude my talk with the same image that I did for my Mount Wilson Observatory science talk, looking out from the 200-inch dome at the great epic Palomar open house, which should be repeated but won't be, in 2005, going all the way out to the tail end. But I looked through my 2005 pictures and I found one which I think that docent standing at the far end of the picture is the legendary Mike Burton. I know he was there, and I think that's a picture of him actually there in 2005. And so since Mike has 20 more years, to work on, I just thought I would honor his commitment for the 20 years he's put in so far. And with that, I'm done. And thank you. I return control to your host.
Tim, thank you very much. And also, thank you to Mike Burton as well. With that, everybody, please turn on your microphones and let me open the floor for questions. Anybody?
Well, that is me at that open house, and actually, I think my wife is there too. I'm at the as you're looking at the picture, I'm at the left side. There's a woman in a denim shirt. I think that's my wife.
Uh-huh. Are you wearing the same hat as you are now?
No, I do have that hat actually. In my closet, in my hat hall of fame.
Okay.
I'm wearing, let's see what I'm wearing today. I'm wearing actually a Bronx High School of Science hat.
Uh-huh. Okay.
So I might point out, I'm not an imager, but there are two of the Planetary Nebula that you mentioned in your talk, Tim, that are great targets for visual observers. One is the Cat's Eye Nebula, and the other is the Ghost of Jupiter Planetary Nebula. And if you're a visual observer, take a peek at those two. They're just lovely targets. You can see them in 5-inch scopes and up. So a good target for visual observers.
I'd like to point out
go ahead.
The cat's eye is particularly impressive to me. See a fair amount of that internal structure in the nebula, but you need a big telescope. Who else?
Other questions, please.
I snowed the whole bunch of them.
Yeah.
Tim, I asked Mendeleev, did he really live to be 103?
Probably he lived for a long, long time.
Because back 150 years ago, to live that long is crazy, amazing.
Let me get back down to my
At the beginning, yeah, it was like,
1820 to 1886 is.
oh no, I saw
Oh
some.
no, that's I can't read the top of my slide, so I
Oh,
can't.
okay. I think it just was shocking to me because there he goes. No, so up in the upper left, 1804 to 1907.
Yeah,
That's
yeah,
crazy.
he did.
Nice to know that looking at the stars makes you live long. Or looking at the elements, I guess it is, not stars. Crazy.
Yeah.
Tim, you mentioned that hitting an alpha with an alpha can give you beryllium 8 and a gamma ray, but the beryllium 8 only lives, no, I forget, I think I wrote down 10 to the minus 17 seconds, something like
There it is.
that.
Yeah.
But there's an excited state, a metastable state that lives at 10 to the minus 17, that lives longer. Are there other elements that have these metastable states that live longer amongst the relatively light nuclei? Do you know that?
I don't really know. I would not be surprised if there are. There certainly is for beryllium. That's what makes this work. But I don't know the specifics of the metastable states for other light nuclei.
And how long is that metastable state in beryllium?
I think the half-life that I've given here is that half-life, but I'm not sure. Because this is 8 times 10 to the minus 17 seconds.
Uh-huh.
So you have time and the fact that you've got to get into this state, both that you have to satisfy to make the fusion work.
So if someone tinkered if nature tinkered with this time and made it 10 to the minus 19 seconds, we wouldn't be here having this conversation, would we?
That's right. And that and the time scale for proton fusion, it's one of the themes of this idea is that not only us, but the physics and time scale of the biggest things in the universe, galaxies, galaxy clusters, galaxy superclusters, all of that depends on the time scales for these nuclear reactions. And if you diddle these time scales, you massively change the astrophysical history of the universe. So the details of how the biggest things in the universe behave is intimately dependent on the details of how the tiniest things in the universe behave.
And those intimate details of the tiniest things have been experimentally derived by machines like the one behind me. When
Yeah.
Tim talks about bashing 2 helium atoms together, well, that's what this machine does. It does it 1 helium at a time and generates beryllium and measures how long it lasts by watching its decay. So these accelerators were used to bash helium into everything, helium into beryllium, helium into hydrogen, helium into carbon, and measure the lifetimes and the likelihoods of those reactions going forward.
Have you duplicated the famous Rutherford scattering experiment?
Well, at Caltech, undergraduates do that routinely.
Yeah. He got a Nobel Prize for it. Now if you're lucky, you get a bachelor's degree for it.
I mean, 2 doors down, I've got the apparatus that Millikan used for the Millikan oil drop experiment, so it's a rich place here at Caltech.
Oh, Tim, let me ask a facetious question,
Yeah.
maybe. You showed
Okay.
a periodic table, and at the lower right, there were elements that have been created in colliders and so forth. And as we get bigger and bigger colliders, maybe we can make even more. I want to ask if these elements are really useful, but the real question is, do they exist in nature, and do we know that? Added in the last decade, I think you mentioned some of them were synthetic.
I think the answer is, if they exist in nature, we don't know it. And the reason we don't know it is that their decay time scales are incredibly tiny, like the beryllium 8. I mean, they're fractions of a second. So even if they happened in nature, if you weren't staring at the right spot at that fraction of a second, you simply would never know that they happened in nature. So the only way you can get to them is to find them in a laboratory experiment. And when I showed you, I'm gonna make everybody dizzy. When I showed you my collection of spectra, you'll notice for most of those elements, there's no spectrum. You could calculate one if you really wanted to do the work, but their half-lives are so short, nobody's been able to observe a spectrum of them. And so we don't know what their spectrum looks like.
That's a really neat chart, by the way.
Hey, maybe Alan knows what their spectrum looks like. He's got this stuff there to make him.
A lot of the spectral lines for the lighter elements were in fact done by places like Caltech, but no, we can't reach out to those heavy ones right now. Not here.
Okay.
I had a question about the HR diagram. You showed the white one with the sun wandering around.
Yeah.
Can you go back to that?
This one?
No, the one which showed our sun in its evolution.
Yeah, that's what this is.
So if it's wandering around off the main sequence line, isn't that out in the area that you said there weren't any stars?
No, this is going up into, it's going up into the red giant area here. So the sun becomes a subgiant, a red giant, an asymptotic horizontal branch around here, and then goes up to the probably up here, and it doesn't become a super giant. It'll be a red giant, and then rapidly moves across, and you might find a white dwarf or two out here. They cool fairly rapidly at first, as you might expect, but then slow down. And the cooling curve for white dwarfs down here is really, really, really long. And you can get the age of a globular cluster by looking at the bottom of the white dwarf sequence in the globular cluster, and then modeling how long it takes to cool that far.
So a star might start in one category and move to another, but does so relatively quickly.
Yeah.
Okay, got it.
Yeah. So the time scales are up here on the top, where the sun is now 4.5 billion years old. It'll take it 10-12 billion years, and this chart is 12.2 to become a red giant. But then you notice the time scale shrinks a lot to go to horizontal branch, planetary nebula. These things happen fast by stellar scales. It's the main sequence and the first trip up the red giant that takes a lot of time. The rest of them to go by pretty fast. And the more massive the star, the faster those steps go by.
Oh, I got it. Thank you.
Yeah.
Tim, what are the details of that textbook that you held up a couple of times?
The Nuclear Physics of Stars.
And the author?
The author's name is Christian Iliadis, and it's from Wiley, which hopefully you can, it looks backwards on my screen. Hopefully it looks forwards on yours.
Thank you.
Okay.
In the chat, there was a question about where neutron stars fall on the HR diagram.
Okay, well, neutron stars don't fall on the HR diagram. at all, just because they're kind of not normal stars. Neutron stars can be extremely hot, but they're super dim. So they would likely fall off the bottom of this plot. And so if you go all the way over to the left and then go down off the bottom of the chart, that's where you would find a neutron star. Because all the stars in the upper part, main sequence, red giants, red super, there's some kind of fusion going on. There's stuff happening. But white dwarf stars, like neutron stars, are just sitting there, cooling off and not really doing anything anymore.
Okay, thank you. Are there, excuse me, are there other questions? Well, going once, going twice. If I could, let me ask a question then to
Sure.
maybe to wind the meeting down, because we are running a little long on time. We've been talking about the origin of the elements, but where does this process end up? You said you wouldn't talk about expansion of the
Well.
universe, but the universe is expanding and it's cooling. Does the process of creating heavy elements from lighter elements contribute to the eventual heat death of the universe?
Directly, probably not. The heat death of the universe, if it happens, is going to be a result of the continued expansion of space-time as the universe gets bigger and bigger and bigger, and things, the clusters get farther apart, and over the billions of years. Now, the sun has a main sequence lifetime of roughly 10, 12 billion years. Way down at the bottom of the main sequence, red dwarf stars, depending on their metallicity, will last from 10 to 100 trillion years. And that's work done by Adams and McLaughlin that you can find in Reviews of Modern Physics. And they wrote a book about it. And I don't remember which way the metallicity influence goes, but it's 10 to 100 trillion years for red dwarfs. So we have plenty of time. But beyond that, there are ridiculous time scales depending on how the expansion of the universe works. Let's see, who was it? Freeman Dyson wrote a paper in Reviews of Modern Physics around 75 or 76, exploring the long-term evolution of the universe. And Adams and McLaughlin followed up with another one. And he came up with a number 10 to the 10 to the 76th year. So the exponent on the 10 is 10 to the 76 years for all matter in the universe to quantum mechanically tunnel into black holes. So that's a really long time. And of course, if that actually happens, you're not done yet, because Hawking radiation is still going to happen. And so you're going to fill up the universe with a background bath of Hawking radiation. And as the black holes are emitting Hawking radiation, which would make you think they're going to evaporate someday, they're also absorbing Hawking radiation from the other black holes. And you're going to reach some kind of equilibrium unless the expansion of the universe eventually makes it so big that there's just one black hole in the whole universe, and it's nothing to, it's crazy. So the root problem is like if you look at a movie and you cut a dozen frames, contiguous frames out of some section of the movie, and you give that to somebody and say, okay, I want you to recreate the movie from these frames. What they will probably do is a pretty good job before and after the frames because they know what's going on. But pretty soon they will have created a movie which has nothing at all to do with the original movie, the frames tape, just some complete fantasy. And that's our knowledge of cosmology is those 12 frames. That's what we know right now. And the rest of it is a complete mystery. The universe could easily stop expanding and contract on itself. You can do that in general relativity without quantum mechanics, but you can also do it in string theory and loop quantum gravity and any other formalism for cosmology. And if you model what they call an ekpyrotic universe, if you have 5-dimensional membranes crashing into each other in a 10-dimensional bulk or whatever, in other words, you can create whatever fantasy you want to explain the Big Bang, and it all works just fine because nobody has a clue what's going on. And so the heat death of the universe may or may not happen. It could be just a complete myth. Who knows? Nobody knows. So that's the best I can tell you.
Well, thank you. That went deep. Thank you very much. I greatly appreciate it.
Good. And thank you, Mike Burton. 20 more years. Yay.
Yay. So, if I could bring the meeting to an end. We're going on an hour and a half. Again, Tim, thank you very much. That was a marvelous explanation.
Good.
Thank you very much.
Well, I hope my flaky internet connection held out.
For the most part, it did. It was cool. And with that, let me briefly mention our next Greenway Talks meeting. Greenway Talks will continue on Saturday, February 18th. Physicist Avi Loeb is Bard Professor of History at Harvard University and Director of the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics. Among a long list of honors, positions, and awards, Professor Loeb is also head of the Galileo Project, an initiative, he argues, that represents the first systematic scientific research program search for potential artifacts or remnants of extraterrestrial technological civilizations. Professor Avi Loeb will lay out the evidence and explain why he believes the interstellar object Oumuamua represents just such an extraterrestrial artifact, our first sign of intelligent life beyond the Earth, and perhaps likely our last. I would also recommend Professor Loeb's latest book, Extraterrestrial, the First Sign of Intelligent Life Beyond Earth, published in 2021 by Houghton Mifflin Harcourt. It's a good read, and he goes through his explanations and rationales very carefully. So with that, Tim, thank you again. And thanks to everyone.
Great talk,
Right.
Thank you.
Great talk.
great talk.
And with that, close the meeting, say goodbye, and hope to see you all on February 18th. Bye-bye.
Bye.
So long, everybody.